Okay, so good evening, everyone. Welcome to the 19th interactive gauge session of NPTEL series. So, in this session, we'll be addressing the topics that were suggested by some of the students in the last session. So, as per the schedule, it is supposed to be something in soil mechanics, but we'll be looking at pressure vessels, shear center, Mohr circle for transforming stresses, plane stress, and also some other doubts that have come up. So we'll be dealing with strength of materials in this session. And before we start, wish you all a very happy new year 2024. And I wish you get all the success in terms of your career for your GATE exam and everything that you wish to do. So this question was thank you for the wishes. So this was the question in the in the in the in the forum. So it's a simple one. You have a pipe of 120 mm dia and 8 mm thickness is connected to 16 mm thick plate. So it looks something like this. So we have a plate and we have a pipe welded to it. And they have mentioned that uh, it is welded all along its perimeter. So if you look like this from this point, the pipe looks something like this. And the weld surrounds the pipe. So the weld is uh, somewhat like this. Now, if we take a section, it looks. Let me just draw the upper half. So in section, it looks something like this with weld here. And this is a line of cement. So the bottom is just the mirror image of this. It may be welded on both sides. We don't know exactly, but it's a fillet weld. So it is not right at right at the interface. It is along the sides. So we are given that this plate thickness is 8 mm. So diameter is 120. So this should be 60 mm. And then this plate thickness is 16 mm. Now again, as usual, we need to filter out what is the data that is required for solving the problem from what is the other data. So they have directly given the stresses. The weld is subjected to combined loading, and it is found that the resultant shear stress of magnitude something and bending stress of magnitude something are acting on the weld. So here we don't have to analyze the weld group for internal forces. They have already given the stresses. So typically, this is an out of plane connection. Sometimes we may have to find out the stresses. We will just give the shear force and bending moment and the axial force, and we may have to find out the stresses in the weld, but they have already given the maximum, the resultant shear stress and resultant bending stresses. So, so we don't have to do the analysis. We are directly given the stresses. So this diameter is a useless information. The geometry of the weld is not useful. We are only interested in the stresses in the weld group at a given point. So what we actually need to analyze is only the weld group. If we take a small element of weld group, they have already given the stresses on this element. So we have an element of the fillet weld like this. This is subjected to an axial force because of bending. The bending stresses are something like 500 by T Newton per mm square. And it is subject to some shear stress of, so it can be like this, 150 by dE Newton per mm square. Now this is all that we need to consider. And they have given that the effective throat thickness, the constant K is 0.7. So what does that mean? That means that this is a perfect triangle. If the weld is like this, we know this is the throat thickness, the minimum length, right? The minimum area in the weld, that is the throat area. So this is the throat area. And if we have a perfect isosceles triangle, this side is S, this side is S, So this will be S by root 2. And S by root 2 is approximately 0.707 S. And this is usually taken as 0.7 S. But usually wells that are made in the field are not perfect isosceles triangles. It may be something like this. So in that case, this factor K varies. Here, this is the factor K. For other weld geometries, K is different, but they have asked us to consider K equal to 0.7. So this is all the given information in the question. What are they asking? They are asking what is the minimum size of the fillet weld. So if we have a fillet weld like this, the distance along this, right, the the distance of this prism, that is the length of the weld group. This side of the isosceles triangle is S, and this is the size of the weld group. The smaller one of the two is called the size of the fillet weld. And this, as I said, it's the throat thickness, the minimum thickness, the critical plane, right? So if you have a plane of minimum area within this, that will be this, and that will be the throat area. So this is throat, this is size, and this is length. Now in this question, they're asking the minimum size of the well. So let us see. And what else they have given? They have given the grade of steel is Fe410. So first thing to do is to find out the properties of Fe410. So from table 1 of IS 800, you can see that these are the properties. And if this is the ultimate strength, this is the ultimate tensile stress. So Fe410, these three come under Fe410 grade. And for all these three of them, the ultimate stress is 410. So there directly you can take Fu to be 410 Newton per mm square. So that is one data. And then so if we have a fillet weld, the design strength of the fillet weld is given by this. So we have the material stress is Fu, the ultimate tensile stress is Fu, and you know that under combined loading, so a fillet weld is usually subjected to shear. So if you have two plates, one plate here, another plate here, and it is resisting some force P, this throat area is usually weak in shear. This tends, the forces on a fillet weld are transmitted in the form of a shear. But if it is a butt weld like this, you can have directly, this is transmitted onto the weld directly as a tension. But in the case of a fillet weld, it is always in the form of a shear. And the assumption is these welds behave, they are extremely strong materials as compared to the parent steel. The weld material is usually very strong. And the assumption is that they behave linear elastic until failure. So at some point, which is Fu, they fail abruptly. So until this point, they remain linearly elastic. So the stresses can be transformed onto this plane. So the von Mises-Leal criteria, something similar to that is assumed. And the equivalent of von Mises stress, the equivalent von Mises stress is given as, if you remember, it is if you just consider one plane, it is sigma xx square plus so it is something like sigma xx minus sigma yy the whole square plus sigma yy minus sigma zz the whole square plus sigma zz minus sigma xx the whole square plus 6 times sigma xx sigma xy square plus sigma uh, yz square plus sigma xz square. This entire thing divided by 2. Everything is under the root. So this is the equivalent von Mises stress which is used in plasticity. And for simple cases, or if you have something subjected to pure shear tau, then all these vanish. Right? You just have one term, everything else vanishes. In that case, if this is the yield stress, if you use von Mises yield criteria, so the von Mises stress will be just square root of 6 by 2 is 3. It is just 3 tau square. So if this we treat as the failure stress, So what does the one misses criteria say? So it says that when the distortional strain energy equals some critical value, the material fails. So this is the equivalent uniaxial failure stress. This is what is corresponding to. So this material is subjected to some multi-axial loading. You have all kinds of stresses, sigma xx, xy, yx, and all. But we don't do material testing under complicated states of stress. So we just take a uniaxial tension specimen and find out at what stress that fails. Let that stress be sigma Vm. How do these? How are these two related? These two are related by this expression. That is exactly von Mises criteria. And if something is subjected to pure shear, the relation is this, which says that the failure stress under shear is something like the failure stress under tension divided by square root of 3. So this is just the background. Now you can recall what this is. So Fu is the ultimate tensile stress, which means under tension, the coupon fails at Fu. But fillet weld is usually subjected to shear along this plane. So the shear stress on this plane should not exceed Fu by square root of 3, because when the shear stress reaches Fu by square root of 3, the maximum tension on some other plane would have already reached Fu. So the material will break. So the yield, the design stress, the design strength under yield is Fu by root 3 divided by this partial safety factor, material partial safety factor. And this partial safety factor is 1.25 for shop welded structures, and it is 1.5 if the welding is done in field. So this you can always check in table 5 of IS 800. Now this is for pure tensile loading, just for one fillet weld. If it is subjected to a combination of stresses, the criterion is something like this. Because when you have, so this we have just considered one case, but usually you can have both axial force and shear force on the weld. In that, in such cases, this is the formula to be used. So this again comes from von Mises criteria. So 3q square is nothing but the q is the net shear force on the weld. So if this is the weld, you can have a net force in some direction, right? There can be a net force in some direction divided by the throat area, that is q. But the weld itself may be subjected to some axial force. So that is Fa. So Fa is the axial force or the bending forces that are coming onto the weld, and Q is the shear force onto the shear force in the weld. Since the state of stress in the weld is very complex, the exact state of stress is usually unknown. So this is just an approximation to check the safety. So this, when the axial stresses can interact with the shear stresses, something like this is used. So we have all the data to solve the problem. Now let us just write this down. We are already given what is the bending stresses. So Fa is, you recall, it is 500 by the throat area. And Q is the shear stress, which is 150 by throat area. And both are given in Newton per mm square. Now, what is the next step? It is under a combined state of stress, combined loading. So we have to check this criteria, right? Individually, they have to obey this. That is, individually, the forces divided by the throat area should be less than Fu by square root of 3. Not only that, they should also satisfy this criteria. So if this is satisfied, automatically those two will be satisfied, as you can see. If these are positive numbers, so that will be automatically satisfied. Now let us check this criteria. What is Fa square plus 3q square? So here it is 500 by Te the whole square plus 3 times 150 by Te the whole square under root. So this is the equivalent stress which should be checked under combined loading. Now you can find out what this is. So it is 500 square plus 3 times 150 squared. So let me take square root as well. So if we take square root, it is about 563 by 563.5 by TE Newton per mm square. And what is FU? FU is 410 Newton per mm square, right? And what is FNW? The nominal strength of the fillet weld. It is 410 by square root of 3 because fillet weld is usually loaded under shear. So this is about 236. 230, let's say 236 material strength, right? So 236 Newton per mm square. And we also have the partial safety factor for the weld as 1.25. Therefore, the design shear strength of the weld is again 236 Newton per mm square divided by 1.25. Because again, they have mentioned in the question it is shop welded, right? Somewhere I saw it is shop welded. Yeah, shop welding. So it is 1.25. If it is field welding, it's a different number. So this is about 189 Newton per mm square. And then this number, so this has to be less than or equal to this. So let us put that condition. So 563.5 divided by TE. This is the load that is coming onto the weld, and the resistance of the weld is 189 Newton per mm square. Both are in Newton per mm square. Just rearrange, you get T is greater than or equal to 563.5 by 189. So this comes to around 2.98 Newton per mm square. Let us approximate it as 3. Sorry, this is not Newton, this is mm. So the required throat area, right? This is the throat area. They have mentioned in the question. T is the effective throat area. So the required throat area has to be 3 mm. But what is the throat area? It is 0.7 times S. They have mentioned the factor K is 0.7 times S. So this should be greater than or equal to 3 mm, which means S should be greater than or equal to 3 by 0.7. So this number divided by 0.7 is about 4.26 mm. So the size of the weld that we should provide should be greater than or equal to 4.26 mm. So is that enough? No. This is what is required for carrying the load. So this is governed by whatever this. This is what is required. This is required. But there is also some minimum that is specified by the code. So in order to avoid cracking under thermal loading or some small fluctuations, the code suggests some minimum where it is. Yeah. So the code suggests some minimum size of the weld. So this is it. So depending on the thickness of the two parts that are connected, the minimum size of the weld is specified by the code. So if the thicker part is less than 10 mm, the minimum size is 3 mm. But if the thicker part lies between 10 mm to 20 mm, the minimum size specified is 5 mm. So in our case, the thicker part is the plate. Right? The plate is of 16 mm thickness and the pipe is of 8 mm thickness. So the thicker part is the plate. Therefore, we need to provide. So this comes under the second row. So the minimum size as per table 21 of IS 800 is this. So 16 falls here. So we need to provide 5 mm. Although for carrying the specified load, we need only 4.3 mm. We need to provide 5 mm to avoid unnecessary cracking and right the thicker. So this you need to provide some minimum. So the larger one of the two is 5 mm. Therefore, we need to provide 5 mm thick weld. So the correct answer is option B, 5 mm. But really, I do feel that this expecting a student to remember this table by heart is a little unreasonable. But that is what it is. If yes.
Understood, sir.
Yeah. So That is the thing. So
Sir,
let me.
ask
Yes.
for maximum size of weld.
Yes.
Sir, then uh, would it be 6.5?
Uh, Maximum size of the weld. Why is the maximum important here?
No, sir, if we were asked in case.
Okay, uh, so I think the maximum size of the weld is governed by the thickness of the thicker part, and it has to be less than 3/4 or something. So let me check. In order to ensure that the uh, usually, so here, mm, this is 16 mm, this is 8 mm. So
सर 8 minus 1.5 ही नहीं कर देंगे उसमें सीधा.
yeah, let me open the code. That is better, not this. Yeah, I think, yeah, this one, right? Yeah, so it is the smaller one of, correct. So if it is a plate, it is, no, but in this case, we don't have an edge, right? So that's not a problem. When we have an edge, that is the, so let us see, where is figure? Hmm. Yeah, so this is only in the case of when fillet welds are applied to edges of a plate or section in members. Here, in this case, we are not applying a fillet weld to the edges, right? So here, we don't have an open edge onto which we are applying the fillet weld. So I think this restriction doesn't apply here. So this one. So when a fillet weld is applied to a square edge of a part, so this should be at least 1.5 mm less than this. Right. So this entire section 4 10.5.8.1 to 5, all this applies only when the fillet weld is applied to the edge of a plate or a section. Here it is not applied to the edge of a plate or a section, so we don't need to worry about this. So I don't think there is a maximum in this case. It is just governed by the electrode, whatever electrode thickness. So all these restrictions apply when we do the fillet weld to the edge. Is that okay?
Okay, sir.
Yeah. So now let's go to the concept of stress transformations. So this is where you had doubts. Mohr circle and shear center. So these ideas are little, the concept of pressure vessels and stress transformations are little related. So we'll have some conceptual problems where we use both the concepts. Right? So it's unlikely you get problems of this hardness and gate, but it will help you solve the, it will help you get your concepts cleared very well. That is one thing. So I also understand both of you are like you most of you are from you're still in your BTech, so understanding these clearly is more important than gate as of now, right? You have another option to do your gate. So let's start. So let us have this little interactive because this I would like to know how much you know about stresses. So we have a body uh, or a structure happen. Yeah. So let us consider you have a body or a structure like this. And what do you understand is subjected to some loads, right? So what do you understand about stress? So we call stress by sigma. How do you define stress? Is it force by area or anything? We have many forces, P1, P2, P3, and so on. Let us assume the body is in equilibrium, right? We are dealing with statics, so it is in equilibrium. And how do you define stress at a point? Or how do you define stress?
So stress is force acting on a unit perpendicular cross-sectional area.
Okay, so that is fine. Uh, so that is where, so right, so I understand. So you defined something like force by area. Now I have a body. So if you have a bar, it is fine. If you have a bar, it is pulled on both sides with a force F, and the bar has a cross-sectional area A perpendicular to the force, then you can say the stress in the bar is F by A. But our structures are not bars. We have things like this. You can have a stone. You can stamp on a stone or something. You can have many forces acting, so acting on the structure, or just take a beam and you're subjecting the beam to bending. You call the stress here sigma to be given as my by I. So what do you mean by the stress here? Because you don't have a force and you don't have a perpendicular area to that, right? The net force on the section is 0. Then how do we get sigma as my by I? So there is something different, right? There is something beyond force by area in a stress. So just remember stress at a point is not force by area in general. It is something more than that. That is one thing to remember. Now, can stress depend on the point we are choosing? So stress here can be different from the stress here. Yes, right? Again, you can take the example of a beam. Beam is some body in general. If you take a point on the neutral axis of a beam, the stress is 0. If you take the extreme fibers, it has got some maximum stress. So stress is in general. The second thing you need to remember is stress is a function of the position where you're looking at. So stress is a field. What kind of field it is? So scalar, vector, tensor, you have that introduction. So you know scalars are just numbers. Vectors, you know, things like velocity, displacements, they're all vectors because they have something like a magnitude and a direction. What about stress?
Tensor, sir.
Tensor, yes. So another thing is stress is a tensor. So we'll see what are tensors. We don't get into the detail, but it is somewhat important. So stress transformations follow directly from tensor transformations. So there are many things that transform similar to stress. One is so stress is a tensor, then strain is a tensor, and there are certain other tensors like moment of inertia is a tensor. So the transformation for all of them can follow from the Mohr circle. So the reason they all transform in the similar fashion is because they are all tensors. Just like how you don't bother if a given vector is a displacement or a force, you just transform it. So okay, let us get to that point. So you have a vector. You have a vector, right? This is just a directed line segment in space. Now the vector can be anything. If I choose a coordinate system like this, I choose a coordinate system like this. These are the components. So suppose this is 3 and this is 2. This vector can be written as 3 times I plus 2 times j. But I can also choose a coordinate system like this. I can choose the x-axis along x. Let us call this coordinate system x dash and y dash. And let us call the original one as x and y. But if I choose a coordinate system like this vector is not going to rotate. This vector is a given line. So if I say a body has moved from this point to this point, this is the displacement vector of that particle. It should not depend on how in which way I choose the coordinate system. So if I choose the coordinate system like this, I say the displacement of the point is 3i plus 2j, where I and j are the unit vectors. So, but if I choose the coordinate system like this, what is the displacement of the point? It is something like what it is. I'm saying this is x dash.
Root of 3 square plus 2
Plus 2
square
square,
I
that is
cap.
39 I cap plus let us put it as I dash cap 0 j dash cap. So how do you relate these two vectors? Those two vectors are related by they are not related, they are exactly equal. So 3i plus 2j is exactly equal to square root of 13 I dash plus 0 j dash. So this is something to remember. The vector is the same. Their components in the ij system and their components in the I dash j dash system, they are different. So depending on how we choose these vectors, these are called basis vectors. their components vary, but the vector does not change. This is the basic idea. Similarly, if we have a body like this, and we have a point and we are interested in stress at that point. So stress, as I said, remember it is a function of x, y, and z. Now the displacement at a point is a vector and you know how it transforms, right? So if you are given in one coordinate system, say u, v, and you want to find out u dash, v dash in another coordinate system, limited by this some transformation like cos theta, sin theta, minus sin theta, cos theta. That you easily derive, right? Take the rotation to be theta, and then you can relate. For a general vector, take the components, you'll get along this, you'll get u cos theta plus v sin theta that you usually do in your physics, first year physics. So that is very simple. Similarly, there are some ways in which vectors, tensors transform. But we are not going to get into that detail, but we will see why stress transforms in a given way. We have stress at a given point. Now, a point has got zero area, so the definition force by area does not work. So we need something more. So here is the understanding, right? So you take a body. There are forces acting on the body. Let us just take 4 forces, and these 4 forces, as you can see the way I have drawn them, they are depending on some magnitudes, they keep in equilibrium. Right? They are concurrent, so they keep the body in static equilibrium. But this is a deformable body, so it would have deformed something like this. Or let us take this to be actually the deform configuration of the body. Now under this action, you take a point P, and we are interested in stress at this point. So the stress at this point is not F1 by A, it is not F2 by A, it is not any of these. It is something more. Now let us see how that is, what it is, right? So this is a little important. Now these are external forces. The body is deforming, which means the atoms are coming closer, right? It can come closer or away depending on the local deformation. So the atoms, so if you have a lattice, the bond length will change under the action of some forces. The bond length may change. So as the bond length changes, there is some internal forces. So these are external forces, but what if you remember some of my older sessions, I said if a structure is in equilibrium, every part of the structure must be in equilibrium, which means if I cut the body into two, then every half should be in equilibrium. Now, if I cut it into two, these are the external forces. But if you see, these are not enough to keep the body in equilibrium. This will just fly apart, which means this part is applying some internal forces on this part. So there are some internal forces on this face. So if we cut the body, there are some internal forces which are counteracting the applied external forces on every segment of the body. Therefore, so now we have got a plane and we have got some internal forces. Now we have a point here. So this is the point P. Now this point P is associated with some area, right? When you make a cut, this point P is associated with some area. Now consider the limit. So there are some distribution of internal forces. So similar to a beam, if you have a beam, you have something called a moment. But in reality, in Newtonian physics, you don't have moments, right? Moment is there is something. Moment is moment of a force. We have only particles, and forces can act on particles. So on this section, there are many particles, and each particle is supporting some internal force. Who is applying the internal force? The other part of the beam, right? This part is applying some forces on this. This part is applying some other forces on this, and they are in accordance with the Newton's third law. They are equal and opposite, and those we call as the internal forces. There are very many small forces whose net result is a shear force B, and whose net moment, if you take their net moment, that is the bending moment in the beam. Similarly, you have many small forces here, whose net resultant, if you take, will be some force F, and it can have some moment. Now, the idea is you consider smaller and smaller areas enclosing this point. So you take the limit of an area element. So suppose this is an area element containing this point. shrink the area very small. Shrink the area to a very small point, small area surrounding that, and consider the ratio of the force by that area. This is actually stress. Right? So that is very important. It's a very important thing to know. You have something like this. You have a point where you're interested to find the stresses. You cut it at that point. You will expose the internal forces. Now you consider areas. So this is the point and this is the plane. You keep considering. So this is area delta A. You shrink this area to a very small point. So if you consider a big area, there'll be some number of small forces acting on that area. And you shrink the area a little bit, you will have fewer forces acting on that area, and keep doing this. And this limit sigma, the ratio of the force on that area divided by that area is something like stress, right? It is not exactly stress. It is called traction. It is called traction. So is traction a vector or a scalar or a tensor? So force is a vector. So if you have a small area, there is a force vector on that, which is delta F. This is the area delta A. This is the point P. This delta is surrounding the point. This point is lying in this area. The hypothesis is this limit exists. If this limit doesn't exist, then the stress is infinity, right? So that is not the case. As for most cases, when the forces are very smooth, this limit exists. And this ratio delta F by delta A is called traction. So this is a vector. This is a vector. Therefore, this traction, let us call this T. Traction is also a vector. Now, how? So this is something called traction. Now, what is stress? So we have got, if we expose a plane, let us call the plane N, and you consider shrinking areas, the ratio of delta F on the plane N to the area as the area tends to 0, that is the traction on this plane N at the point P. So this is the definition of traction. Now there is some relationship between so this is in general any plane, right? So you can pass through a point, you can have infinitely many number of planes. But let us look at the important planes. If our Cartesian coordinate system is something like this, X, Y, and Z, the three important planes are the XY plane, the YZ plane, and the XZ plane. So this is one plane, this is one plane, this is one plane. So through a given point, you can pass these three planes. One is this plane. Let us call this X plane. You can pass, this is the Z plane, right? It is perpendicular to the Z axis. You can pass this plane, which is perpendicular to the Y axis. This is Y plane. And you can pass a plane like this. A plane like this, which is perpendicular to the X axis. This is the X plane. All these three planes are passing through the point P. And in each of these planes, we can do the limiting thing. So now you have two things to consider. One is on which plane the force is there. So this is a vector. So it has three components. So you can have on N plane, you can have X component. On N plane, you can have Y component. On the N plane, you can have Z component. So these are the components of traction or the stress vector. Earlier, people used to call it stress vector, but it's unnecessary confusion. Stress is a tensor, traction is a vector. So on the N plane, which is inclined at some direction, the X component of the force is Tx. Now replace this N with X. So that is what we are interested in, right? These are the three important cases. So the traction on the X plane, which is the plane perpendicular to the X axis, in the X direction is the stress component sigma xx. Similarly, the traction on the X plane in the Y direction is sigma xy. And the traction on the X plane in the Z direction is sigma xz. So these, how do you call these? These you can call as sigma nx. This is sigma ny. This is sigma nz. So the first index refers to the plane on which we are looking at the internal forces. The second index refers to the direction or the component of the internal force. So that is clear. I hope I'm clear up to this point, right? Is that okay?
Yes, sir.
Yeah. Now let us come to transformation. So you have a body, you have a point. At that point, I can do this thing, right? I can consider planes like this. So if you consider an element, you have this is the so if I consider just a 2D case, this is x, y, z is suppose it's prismatic or something. This is the x plane. You can have force on this plane in the x direction, which is sigma xx. But the traction also have so traction, but let me draw traction like this. And here something like this. So this has a x component which is sigma xx, and on this plane you have a y component which is sigma xy. Here you have an x component. So the positive direction is usually considered. So this is sigma on the y plane in the x direction, and this is sigma on the y plane in the y direction. So these are the shear stresses, and these are the shear stresses. This is sigma yx. This has to be equal and opposite. This is x. This is xy, and this is yx for equilibrium. So you know all this. This has to be equal and opposite. So this is how you define stress at a point. So stress is not forced by area. Stress is the limit delta F tends to delta A, where delta A is chosen this way. So delta A is you make a cut, you expose a plane, you consider smaller and smaller areas enclosing that point. What do you get? You get this ratio. That ratio is nothing but a vector called traction vector. And the traction vector depends on which plane you choose. You can take any plane through that point. You can take a plane like this. Let us call this N1. This is N2. You can take another plane like this. This is N3. On each plane, the internal forces are different. Why are they different? Because that correspond to a different part of the body, right? So N1 gives you a half like this. N2 gives you some other half, right? N2 gives a half like this. So the internal forces will be totally different. So this ratio is the traction. Traction has three components. Let us call them T and X, T and Y, T and Z. But if you choose the plane N to lie perpendicular to the coordinate axis. So this is the Z plane, this is the X plane, this is the Y plane. If you choose these planes, which are most important in problem solving, then what you get are the stresses, sigma xx, xy, and xz. Now here is where the transformation is important. So as I said, for a vector, it doesn't depend. The vector is independent of which coordinate system we use to describe it. Therefore, the tensor is also independent of the coordinate system. So the stress at a given point should not depend whether I'm choosing to cut along x and y or I'm using some other x dash and y dash. Correct? So the stress at this point should be invariant. If so, that is basically I shouldn't get two different values of internal force vectors if I just change the coordinate system. So this invariance, the fact that the forces should not change gives us the rules of transforming stress components from one coordinate system to another coordinate system. So here the simplest thing we can do is this is a small element of stress in 2D. So this is sigma xx, sigma yy, sigma xy, sigma yx. And you know those two are equal because you want to preserve angular momentum. So if they are not equal, this element can rotate. So based on the requirement of angular momentum, the stress has to be symmetric. So sigma xy should be equal to sigma yx. This you know very well. So this is sigma xy. Sigma xx, this is sigma yy. That is called the sigma xy. Now this is the point P, and this is the state of stress. But there's nothing that says that my cut has to be like this. I can also cut like this. That is, I can cut perpendicular to another axis x dash. So you can think of a cut like this. So this is your x-axis, and this can be your x dash axis. And if you cut perpendicular to that, you will expose another face, which is this. And these two are the original faces. Now, what are the, let us call this as x dash phase because it is perpendicular to x dash. What are the components of traction on the x dash phase? So perpendicular to x dash, I can have a y dash axis, and perpendicular to x, I can have a y axis. So here the stress components are sigma, sorry, is- let me, I hope I'm audible, right? There's no noise.
Yes, sir.
So, so this is your sigma, this is your sigma xx, and on this space you have sigma x dash, and this is your sigma xy. The space on x dash phase in the y dash derivative have sigma x dash y dash. Now, if this angle is theta, so if this is in one plane, so the transformation can be related by some angle theta. If this angle is theta, this angle is also theta. So the areas are related as, so if you consider limiting areas on the x dash phase, so let us say this is dy dash because it is in this direction. This is dx, this is dy, and this is angle theta. So those three are related as, say, dx dash cos theta is equal to, sorry, you just have dy dash. So dy dash cos theta is equal to dy, and dy dash sin theta is equal to dx. This is one relation. Now this small element has to be in equilibrium. So this is the force per unit area on this phase. So sigma xx multiplied by dy. So you just have to establish equilibrium of this element, right? So basically, you just need to this small element has to be equilibrium. That is what you need to enforce. So this is one coordinate system. This coordinate system means the stresses in this coordinate system describe the internal force intensities in force per unit areas, but where the areas are oriented along this, you make a cut in the body along these planes, and you find the force intensity, right? Force intensity. So this you can relate. This you can relate. Sigma x dash. I'll just do one of them, and then we can just go. I'll write down the Mohr circle equation. So let us say establish equilibrium along the x dash direction. So here the force is sigma xx dy. So sigma xx dy. What is this angle? You can. So this angle is theta, right? So sigma xx dy cos theta. And then this is a component along this direction. And sigma yy has a component sigma yy dx sin theta, right? Plus sigma yy dx sin theta. And these also have a component. So sigma xy on the dy phase cos theta. So you have, sorry, sin theta. So plus sigma xy. So this I'm finding the net left force, the net force along minus x dash axis, minus x dash axis. Because we know along positive x dash axis, there is only one force, sigma x dash x dash. All the other forces should, the minus x dash component of all the other forces should be equal to this. So that directly gives us sigma x dash in terms of sigma xx, sigma xy, and sigma yy. So this, if you do this, will be sigma xy dy sin theta, and the other one gives sigma xy dx cos theta. Now just plug in these two. So this is the net force along the minus x dash axis. This should be equal to the force along the plus x dash axis. What is that? That is sigma xx dx dash. Sorry, dy dash. dy dash. Now just substitute these into this. So you directly get, you can take dy dash common here because dx and dy are in terms of dy dash. Get sigma xx cos square theta plus sigma yy sin square theta plus sigma xy cos theta sin theta plus sigma xy sin theta cos theta plus 2 sigma xy cos theta sin theta is equal to sigma xx dy dash. The dy dash you can cancel on both sides. So you already got sigma x dash in terms of the old stresses. So this is the first transformation equation. So similarly, you can establish equilibrium in the y direction, right? You can establish equilibrium in the y dash direction. So this you have considered an axis like this. So that will give you all the so by establishing the equilibrium of this small wedge, you can derive the stress transformation equations. So that's so I got one of them. You can do the others as others in your home. You can try out the others. So the basic equations are sigma x dash is sigma xx cos square theta plus sigma yy sin square theta plus 2 sigma xy cos theta sin theta. And similarly, sigma, so this describes how so sigma xx, yy, xy are the components of a tensor sigma. So sigma is some tensor, it is some mathematical object, you don't need to worry about it. Just like you don't, so if T is a vector, it has components Tx and Ty in a specified coordinate system. Similarly, sigma, if it is a tensor, it has components sigma xx, xy, yy, and so on. It has 9 components in a specified coordinate system. If you change the coordinate system, the components will change, but the tensor does not change. Similar to a vector. So the displacement of a point is a vector. It doesn't matter which coordinate system you use to describe the displacement. The components of the displacement will change depending on the coordinate system, but the displacement itself will not. Same here. So if you go from a coordinate system x comma y to x dash comma y dash, by a rotation theta, right? If original x-axis is this and the new x-axis is rotated by an angle theta, this is the transformation equations. So you have sigma yy cos square theta plus sigma xx sin square theta minus 2 sigma xy cos theta sin theta. And sigma x dash y dash is related to this as sigma yy minus sigma xx cos theta sin theta plus sigma xy cos square theta minus sin square theta by 2. So sin square theta. So this is basically the transformation equation. Now the idea in Mohr's circle is you just replace this cos square theta sin square theta with the half angle formula. So in place of cos square theta, you write it as 1 plus cos 2 theta by 2, and sin square theta is this is 1 minus 2 sin square theta is this one. So it is 1 minus cos 2 theta by 2. And then, yeah, cos theta sin theta is sin 2 theta by 2. Now just plug in these, you get sigma x dash is, so you get a 1 plus cos theta, 1 minus cos 2 theta. So just combine both, you get sigma xx plus sigma yy by 2 plus, so here you have a positive and you have a negative. So you get sigma xx minus sigma yy by 2 cos 2 theta, right? And this is just sigma xy sin theta plus sigma xy sin 2 theta. And in the second case, sigma yy dash is same thing, sigma xx plus sigma yy by 2 minus sigma xx minus sigma yy by 2 cos 2 theta plus sigma xy sin 2 theta. And sigma x dash y dash is what? So this becomes sigma yy minus sigma xx by 2 sin 2 theta plus this thing sigma xy into cos 2 theta. So if you see, you can take this to the left hand side. You can take this to the left hand side. You call this sigma c. C denotes center. Then you get some, and you square and add them. you get sigma xx prime. What happened? Uh, Let me open it. So, so the basic idea is you just get sigma x dash minus sigma c is equal to something cos theta plus something sin 2 theta, right? So this is the key result of Mohr circle. So this, so now how do you show that this is a circle? So you subtract these two. You take sigma x dash minus sigma c and sigma y dash you consider this first equation. So sigma x dash is some constant plus something cos theta plus something sin theta, and sigma x dash y dash is the same thing sin theta plus the other thing cos theta. So this describes, if you square and add them, you get the equation of a circle, so that you can easily check. So subtract this, you get sigma x dash minus sigma c, the whole square. Square them, so you get this square plus this square plus the cross product, the mixed term. You square this, you get this one square plus this one square plus the cross term. Add both, these two gets cancelled, and then you get and then you get sigma x dash y dash is, so let us say this is so this becomes, let me write it down. So this is sigma x dash minus c. And this is sigma x. This is y minus x. So let me put a minus sign. So if you just square this and add, you get sigma x dash minus sigma c the whole square plus sigma x dash y dash the whole square is equal to this one squared plus this one squared will be just the same, right? So this is sigma xx minus yy cos square 2 theta plus sin square 2 theta. You will get this sigma xx minus sigma yy by 2 the whole square plus you get this one square plus this one square, that is again sigma xy the whole square plus the cross term. So here you get a 2 sigma xx minus yy by 2 cos 2 theta sin 2 theta sigma xy. Here you will get exactly negative of the term, so those two will get cancelled. So you get a 0. Now this is not, so this is in the form of a circle, right? So if this you call it as your x, this you call it as x naught, this you call as y, and this you call as r. So you get x minus x naught the whole square plus y minus 0 the whole square is equal to r square. So this is in the form of a circle. So basically, you can write down the stress transformation as so. So what this means? Well, so the idea is you have a point, you have some state of stress sigma xx, sigma xy, sigma xy, sigma yy. You make a transformation from the existing coordinate system to another coordinate system by rotating it by an angle theta, that is sigma x dash y dash. Then what does it mean? It means that the components of the stress will become something else, sigma x dash, sigma y dash, and so on. But what are those components? Those are related to these by some transformation relation, which is this. it is this. How did we derive it? That is by considering equilibrium of a wedge element. But it turns out that they correspond to the points lying on a circle. So if you have a plane stress condition, that is, you don't have any z components. If you just have a 2D state of stress, all the stress states correspond, all the components, depending with regardless of which coordinate system you use, all the components lie along a circle, centered at a point sigma c comma 0, and with a radius r. So this is a point sigma xx comma sigma xy. So if you have a point like this, so a Mohr circle describes a stress state. Mohr circle is equal to a state of stress. It's a coordinate-free representation of the state of stress at a given point. That is the idea. You don't want to describe the state of stress. So if you give the coordinate system and give the components, it describes the state of stress completely. But when you go to a different coordinate system, you don't need to recalculate all the stresses again. You just have to transform the stresses using the relations. But those relations basically mean you just move on the Mohr circle. So if this is a point sigma xx, sigma xy, and this is a point sigma x dash, sigma x dash, y dash, and those two are related by a rotation 2 theta on the Mohr circle, then they correspond to two different elements oriented at an angle. So this is xy, and this is another element x dash, y dash. The angle between these two coordinate systems is theta. So if you rotate the coordinate system by an angle theta, the components of the stress tensor will transform according to some transformation law. But that transformation law can be easily represented in the form of Mohr circle, where centered at sigma c. Sigma c is just the average of these two principal stresses, two stresses, and you have a radius which is sigma yy minus sigma xx by 2 the whole square plus sigma xy the whole square. These two are invariant, right? This is also something important. You see, whichever the circle is the same circle. It does not depend on the center of the circle, and the radius of the circle does not depend on which point on the circle you are on. So regardless of the coordinate system, this sigma c and r are fixed. So the Mohr circle can be used to quickly compute the stress transformations in the case of plane stress. If you have a three-dimensional state of stress, you need to do something more. But as long as you have all the z components equal to 0, the Mohr circle is a very powerful tool. So one of the key applications of stress transformations is pressure vessels. So if you see pressure vessels, what just happened? I can't see. Okay, no problem. I'll just copy these slides there. Yeah. So let us again, today is New Year, right? So let's have it a little bit. So pressure vessels are basically some structures that enclose a pressurized gas or pressurized fluid in general. So the best examples of pressure vessels you would have seen in your childhood are balloons. So a balloon encloses pressurized gas and the balloon is stretched. So what is so the key idea? How do you know the gas inside the balloon is pressurized? Because if you open this knot, the gas immediately comes out, right? So gas moves from high pressure to low pressure. So the pressure inside the balloon is obviously of higher pressure. But what makes the gas pressurized inside the balloon? So again, let us do a simple analysis of this balloon. As I said, let us cut the balloon here. If you just ignore well, let us consider air. So air has got very small density. So, and initially it is in static conditions. It is in equilibrium. So you don't have any acceleration. You don't have any flow of gas. So so you know, right? The pressure has to be hydrostatic, and if the balloon is very small, the variation is not too much. So the variation is not too much. Rho is small, h is small, so you can consider the pressure to be constant P. And outside, you can always normalize the atmospheric pressure to 0. Now, if you cut the balloon here, everywhere you have a hydrostatic pressure state, right? There is a pressure P inside, and there is 0 pressure outside. Now, what keeps the balloon in equilibrium? So you have clearly you have an unbalanced force. You have pressure P from inside. You have pressure 0 from outside. So what is it? It's missing. What is missing here?
Sir, weight of balloon.
No, that is negligible, right? So let me put it this way now. I can also cut a section like this. I can have pressure everywhere inside. And outside, I don't have any pressure. So by Newton's laws, it is supposed to accelerate in this direction. But a balloon doesn't run away by itself, right? Balloon, if you place it in a place, although it has got excess internal pressure, it doesn't come out. So we are missing a key important thing, that is the internal forces. Right? We have cut the balloon here. We have made a cut here. Whenever you make a cut, you have made a cut here. The cut is passing through some material. There are atoms here. When you cut here, these atoms will have dangling bonds, which were initially there. So these are internal forces. If you sum these, there will be some internal forces. And you can easily see the balloon is stretched. So these internal forces are in here in tensile. Internal forces are tensile. So the tension, you take a balloon, it is initially not, there is no tension. You blow it up, then the balloon gets stressed. What causes the stress? Because you are pulling the material apart, the atoms tries to pull. So there are some internal forces. Those internal forces have a net tension in this membrane. So this is also called membrane action. What are these internal forces acting against? These forces are acting against the pressure inside, pressure of the fluid enclosed. So this is how pressure vessels work. So balloon is the best example for a pressure vessel. Although it is not a linear elastic pressure vessel, it undergoes very large deformation, so you can't use linear elasticity. You can find out the stresses in the balloon by simple cases, but the strains you cannot. Strains, because from this size it goes to something very large, so you can't find the strains, but stresses you can actually compute. Now, cylindrical pressure vessels are similar to the long, small, these cylindrical pressure vessels are, say, you have balloons like this, right? You have balloons like this. Now you make a cut. You can assume the stress distribution. So there are always internal forces in the balloon. So the key understanding is there is pressurized gas. Outside there is 0 pressure. This pressure difference has to be maintained without the balloon bursting or running apart on itself. So there should be internal forces. And where are the internal forces? Those internal forces are in the membrane of the balloon. And you just assume the membrane to be very thin. So if the balloon is very long, you can assume the internal forces are kind of the same everywhere. So except near the edges, anywhere in between you take, the internal forces will be kind of same. Because if you move from this point to this point, nothing changes much. So the forces are not going to change much. That is some crude understanding. So if I take the cross section of the balloon, I am cutting it at half. And the cut is exposing these two faces. And it's exactly half. So here there is some force. There will also be shear forces, shear tractions like this. So that is important. And we have internal pressure. Outside there is no pressure. So this is the free body diagram of the pressure vessel, pressure vessel or the balloon. So here let us say the balloon has some tension T and T. This has to be because why these two should be equal? Because the balloon is symmetric. And if the balloon is symmetric, the shear forces has to be equal and opposite. We'll see if we really have any shear forces. So if the balloon is very, very thin, you can neglect the shear forces. The balloon is also symmetric like this. So you cannot sustain a shear, right? This is a line of symmetry. This is another line of symmetry. So along a line of symmetry, you cannot have shear forces. Why? Because if it is a line of symmetry, on this face you have forces like this. On the other face, you need to have equal and opposite forces. But this is a line of symmetry, which means you can flip these two like this. And the force direction should not change, but they will change. So therefore, these forces have to be zero. So there are no shear forces here. You only have membrane stretching on this face. We have made a cut, we have exposed the unknown internal forces, and those two internal forces are equal. We are not really interested in how the internal force distribution is. Internally, the stress distribution can be something like this, but right now I'm only looking at the resultant, which is the net tension in the balloon. So this is the membrane of the balloon, and these are the forces. Now, this is also a column of fluid, right? There is gas here. Let me draw the free body diagram of the gas also. So there is on the gas, there will be equal and opposite pressure. But it is a gas, and it's under hydrostatic conditions, negligible weight. So if you consider a gas volume, from all sides it is equally, the pressure is equal, right? That is the basic principle of a gas. Under static conditions, it doesn't depend on the direction. Pressure is hydrostatic, means it doesn't depend on the direction. You just have pressure at a point. This is a key difference between stress and pressure. So stress is something that depends on the normal, on the plane in which you are cutting, and the direction. So stress has two components, sigma x, y, something like that. But pressure at a point in a given fluid is just, you take any cutting plane, you take any direction, you take any cutting plane, you have forces only normal to that direction. So on this surface, force acts only normal to the direction. So that is actually pressure. That is not stress. Similarly, on this face, you have only force in this direction, which is pressure. That is not stress. So what is the total? So the total forces have to be equal. So here you have some pressure. Here you have some pressure. So what is the total? The net upward force should be equal to the net downward force. So the net downward force on this fluid column is the same as the net upward force on this pressure vessel. So this is a solid part. The net upward force on the solid part, these are internal forces, right? So these two are internal forces. They should be equal and opposite. So the net force here should be equal to the net force here. What is this? So the diameter of the cylinder, let it be 2r, right? This diameter of the cylinder is 2r. So the pressure, and let us take any length. Let us take some length L. So the area on which this pressure acts is 2RL. And the gas pressure is P. So it is P into 2RL. That is the net upward force on the pressure vessel, on the this half of the pressure vessel. The net downward forces, this is net upward force, this is 2PRL. The net downward force is 2T. So just equate 2T is equal to 2PRL, which means the tension in the cylinder should be equal to, this is tension per unit length, right? This is all, we are interested in this tension per unit length. So never mind. So this is tension. If you consider a length L, it is 2PRL by 2, which is PRL. But we want stress. So the cylinder, if you consider a cylinder, it is axisymmetric, right? You have an axis for a cylinder, and the pressure is independent of which direction you're looking at. Therefore, if you take the tension here, it should be exactly the same as the tension here. Just use symmetry. In structural analysis, you use symmetry, right? If the loading and the geometry are symmetric, then the stresses, internal forces, displacements, everything is symmetric in linear elasticity. So same thing applies here. Regardless of which direction you make the cut, the tension has to be equal to TRL. And it doesn't matter where you make the cut also. Therefore, you can find the stress due to this. So you have a force acting on some area, which is a rectangular area here. So you have a rectangle, of width t. So the width of the rectangle is t, and the length of the rectangle is L. On this, you have a net force T, and you assume this to be uniform. That is the approximation when we come to thin pressure vessels. And this is a very good approximation when you look at structures like balloons because they are very thin. If you look at very thick walled pressure vessels, if you look something like this, then this variation cannot be neglected. There's a quadratic variation, some quadratic variation like this along the thickness. So that cannot be neglected if you have a thick walled pressure vessel. But if the wall is very thin, the variation will be very small and it is approximately uniform. So that is an approximation. The stress at a point is still defined in the same way as I said. You consider smaller and smaller areas and take the ratio of this tension to that area, you get some number. That is the stress at that point. That will actually vary. That depends on the location of the thickness. But if it is very thin, you can average it out. You just look at the average. The average stress in the pressure vessel is T by R in what is the length? It is L and thickness is T. And this stress has got a special name which is called hoop stress. So this is called the hoop stress. You have a pressure vessel. There is pressurized gas. Gas is under compression, right? The gas is under compression under a pressure P. But that will cause the membrane to be under a stress of say sigma H called hoop stress, which is P R L by T L, which is PR by T. So here we have assumed that we have a cylinder. Now, if the ends of the cylinder are closed, this is hoop stress, or it is in the theta direction. So that's not important right now. Just take it as the hoop stress. Now, if the ends are closed with a lid, then what happens? The gas will also push against the lid. So we only consider the gas pressure in this direction. We have not considered the gas pressure in this direction. So the lids will be pushed. What is the total force on the lid? That will be, again, you consider you make a cut here. Now you are exposing something like this. This is closed. This is open. Here the gas is pushing against the lid at a pressure P. Here you again have some tension. Let us call this as longitudinal tension TL. So the longitudinal tension is acting over an area of what? What is the area?
Pi r squared, sir.
No, this is tension. P is acting on pi r square. P is acting on pi r square. This is the tension. It acts only at the boundary, right? You cannot,
Yes, sir.
inside you have air. So what is the area? Area on which the tension acts. So it looks
2
like a
pi
line.
r
2 pi r is the 2 pi r is the length.
into
Sir, 2 pi r into L.
No,
2
this
pi
is
r
T.
into T, sir.
Right. So this length is 2 pi r. This is T. Therefore, it is 2 pi r into T. That will do. So that we can see. But the net tension is P into pi r square. But the longitudinal stress is this tension divided by area, 2 pi r T. So this is P pi r square by 2 pi r T. Pi gets cancelled, r square r gets cancelled. So it is PR by 2T. So the longitudinal stress is PR by 2T. The hoop stress is PR by T. So this is the case of cylindrical pressure vessel. You can also have a spherical pressure vessel. You can have a sphere. You make a cut here. What will be the surface? If you cut a cylinder, you get two points, right? But if you cut a sphere, you get a circle here. And the tension is acting all along this circle. So do the same analysis. You have internal pressure everywhere. And you have a hemispherical ball of gas. This gas is pushing against the membrane at some pressure P. So the membrane is pushing against the gas at some other pressure P. But we know the internal pressure in the gas is the downward part of the gas is pushing against this gas at a pressure P. All this we know. What is the pressure? So this net downward force should be equal to P into pi r square. So the net upward force on this hemispherical cup is, so the net upward force due to the gas pressure on the hemispherical cup is P pi r square. But again, you have internal forces. For some, because of reasons of symmetry, they are going to be same all throughout. Why? Because sphere has how many planes of symmetry? It has 3 planes of symmetry. In any direction, it's spherically symmetric. There is no, so there is, regardless of you choose a coordinate system like this or like this, nothing changes in the problem, right? You can rotate a ball without even knowing it has been rotated. I show a ball containing pressure like this, and then I ask you to turn and rotate the ball in some other direction and show you. You cannot differentiate. Therefore, the geometry has not changed, the pressure distribution has not changed, which means the internal forces also should not change. So they are spherically symmetric. And there are some stresses. Let us call this hoop stress, sigma h. What is the total area on which the hoop stress is acting? So hoop stress is acting on an annular ring, right? You have a ring on which everywhere here hoop stress is acting. So what is the area?
2 pi r into t, sir.
It is 2 pi r into t. This into sigma h is the net downward force, and the upward force is p pi r square. So this is equal to p pi r square. Again, rearrange where sigma h is equal to pr by 2t. So for a spherical pressure vessel, the tension, the hoop stress is pr by 2t, and for a cylindrical pressure vessel, the hoop stress is pr by t, and the longitudinal stress is pr by 2t. This yeah. This is basically the idea in pressure vessels. Let us solve one problem quickly. We are already late, but it's okay. If we stop here, it's a bad place to stop. Let us solve this problem. Or this problem. This is a nice design problem which involves both pressure vessels concept and Mohr circle concept. Let me. So we are building this problem. We are trying to build pressure vessels. So we are taking squares like this, and then you're arranging them to make a cylinder, roughly something like this. And you make many of these. So that is how these cylinders are constructed. These are closed pressure vessels. So square plates of 16 mm thickness. So these plates have 16 mm thickness. They can be bent and welded together. So here you need to put welds. This is similar to what the first problem we solved. Note to form cylindrical portion of a compressed air tank. So inside there is some pressurized air. Now it is known that the allowable normal stress perpendicular to the weld is 65 MPa. So assume that they are butt welded, right? So you have a square like this, you have butt weld and you have the next square. So when the stress across the weld exceeds 65 MPa, this will break, which means the tank will blast. It will blast and all the whatever gas is inside that will come out. So what is the largest allowable gauge pressure in each case? In one case, they are putting the squares like this. In the other case, they are putting the squares in a diamond form. Now, solution is just 2 steps. First case, let us find out. What is the hoop stress? PR by D, right? What is the longitudinal stress? PR by 2T. Is there any shear stress? I forgot to ask. So you can have hoop is one direction, longitudinal is another direction. So if you take an element like this, if you take an element of the cylinder like this is the hoop direction. This is the longitudinal direction. So the stress here is something like sigma LL. This is sigma HH. Can we have shear stress? No. Basically, since the cylinder is axisymmetric, if you have a shear stress here, it means the next element will have shear stress downwards. But it is axisymmetric, right? You cannot have a shear stress when this is axisymmetric. It means when you come back, you will have some other value of stress. So that is not allowed. So this is in this condition of principal stress state. Whenever you have shear equal to 0, that directions are called principal directions. Principal stress directions. Which means on the Mohr circle, if you draw the Mohr circle, this one, black. When you draw the Mohr circle of that point, all possible stress components lie on the Mohr circle. But there are two special components here, which corresponds to the maximum and minimum. And another speciality is, so along the y-axis you have sigma xy, along the x-axis you have sigma xx. The shear stress here is 0 because they lie on the x-axis. So here the shear stress is, so whenever shear stresses are 0, it means they are principal stresses, principal axis or principal planes or principal coordinate system. And the stresses on the principal axis are called principal stresses. And the speciality about principal stresses is that they give the maximum and minimum values of normal stress. They give the maximum and minimum. So this is one principal stress which you call sigma 1, which is the maximum principal stress, and sigma 2 is the minimum stress. So physically what it means, you have a body, you have a point, and at that point you have many internal forces. Depending on which direction you cut the body, you have internal forces. But there are certain directions in which if you cut the internal, there are certain directions in which if you cut, the internal forces are maximum. So if you cut along this, the internal forces are maximum in this direction. Therefore, when the structure breaks, it is very likely that it will break along this line. So if it is concrete, the principal tensile direction will dictate the direction of cracks. It will crack or break along this line. So principal stresses are of critical importance in structural design. That is what I'm trying to say. So in the first case, sigma h is PR by T and sigma longitudinal is PR by 2T. And they are actually the principal stresses. Why? The shear stresses are 0. Whenever the shear stresses are 0, they correspond to maximum and minimum. So the minimum principal stress is PR by 2T, and the maximum principal stress is, the minimum stress is PR by 2T, and the maximum stress is PR by T. And it is given that the weld will break at 65 MPa. So this is not going to govern. This is the maximum possible stress at any direction in the cylinder. Therefore, the weld will break when PR by T reaches 65 MPa. Now, just what is the radius? Radius is 5 meters. Thickness is 16 mm. Pressure. So pressure is what? It is 65 Newton per mm square. The thickness is 16 mm divided by radius is 5 meters. No, radius is not 5 meters. Diameter is 5 meters. So radius is 2.5 meters. So 2.5 into 10 power 3 mm. So find out what is the pressure. It is 65 into 16 by 2500. So this is about 0.416 Newton per mm square, which is nothing but 0.416 megapascals, or rather 416 kilopascals. This is the pressure at which it will break. The weld will break. So when the weld breaks, the cylinder will blast. The second case, what happens? The second case, the weld is oriented in this direction. So the normal stress we need to look at is in this direction at 45 degrees. So let us see what is the case. Now again, the pressure is the same, right? So here we need to consider the stress normal to the weld like this. So let us use the Mohr circle. We have the principal stress state. The maximum principal stress is PR by T. Minimum principal stress is PR by 2T. So this is if it is sigma H, this is sigma H by 2, right? This is also sigma longitudinal. So this is the minimum principal stress, sigma H by 2. This is maximum principal stress, sigma H. So draw the Mohr circle with these 2 points. What is the radius? What is the radius of the Mohr circle? Yes.
Sigma H minus sigma L by 2, sir.
Sigma H minus sigma H by 2 is the diameter. So the radius is sigma H by sigma H by 4, right? Half of it. This is sigma H by 2. This is sigma H. What is the center? What is the center?
Sigma H by 4, comma 0, sir.
No. Right? This is sigma H by 2. This is 0.5 sigma H. This is sigma H. So this is 3 by 4 sigma H, right?
Yes, sir.
Yeah. Now we are interested in the normal stress at a direction 45 degrees to the x-axis. So here I'm taking an element like this. So remember, stress does not change. Components of stress will change. So this is, if I take an element like this, the forces are sigma H and sigma L. Now I'm interested in a direction, but now the squares are like this. So here the force is some sigma H dash. Here it is sigma L dash. Now going from here to here, I'm rotating 45 degrees counterclockwise. So I should rotate in the same direction in the Mohr circle, right? So Mohr circle, you remember if while deriving, the angle is actually 2 theta. We had sigma x dash is something cos 2 theta plus something sin 2 theta. So if you rotate the coordinate system by theta, in the Mohr circle, you should rotate by 2 theta. So if you rotate by 45 degrees, if you rotate the coordinate system by 45 degrees, in the Mohr circle, you need to rotate by how much? 90 degrees, right? And what is this point? This point is sigma x dash, some h dash, the inclined hoop stress. But this is not a principal plane. You will also have some shear stress. Let us call it tau, comma tau. So what is the maximum tensile? What is the shear stress here in the rotated configuration?
Equal to radius, sir.
Equal to radius, which is sigma h by 4. What is the normal stress on that plane?
0, sir.
No. Why is it 0? Normal stress is the x coordinate, right?
Yes, sir. 3h by 4, sir.
Yeah.
3
So it is
sigma
3
h.
sigma h by 4. So when you consider an incline, when you put the squares incline, the hoop stress is actually 3 sigma h by 4. Now what is that we need to consider? What is so the failure stress is what? So the stress on the plate has reduced, right? Initially you had sigma h. Initially you had sigma h is equal to failure stress, which is 65 MPa. Now when failure is possible only in this direction, assuming the square is very strong and failure happens only by breaking of the welds. Failure has to happen at an angle 45 degrees. And at an angle 45 degrees, the direct stress, the normal stress is 3 sigma h by 4. And that should be equal to 65 MPa. Again, substitute for sigma h. So 3 by 4. What is sigma h? PR by T, right? P into R by T is equal to 65 MPa. So actually everything else will remain the same. The pressure will just become 4 by 3 times 65 Newton per mm square into 16 mm divided by radius, which is 2500 mm. So what is the thing? It's just scaled by 4 by 3. Support 555. Okay, so the normal stress in this plane is it is 554. So here there is a small, okay. So we actually need to use some failure theories, but let us leave it for now, right? So similar to how we did the design of welded connections, you need to take, so here it will not carry 554, let me tell that. So this will be 555 kPa. That is, if you just have a connection like this, you don't have any weld material, but if and the normal stress across this joint exceeds 65 MPa, if the tank is going to break, then it can take a maximum pressure of 555 kilopascals when you orient the squares in this way. So that is it. So in this case, you get 416 or whatever. What was it? Now 416 kilopascals, the maximum allowable pressure. And here it is something like 555 kilopascals. So this is how you solve problems in pressure vessels. So I hope this problem helped you look at both the pressure vessel side of things and also the stress transformation. You can ask if I've taken too much time today, but it is an important topic. So if you have any doubts, you can ask me. Sorry for the delay, but it is important, right? Is this?
सर
Yeah.
इसमें फेलियर प्लेन होता है?
You're asking, is this a failure plane or?
Yes, sir. Like, do we have to draw a failure plane, or where it is if we are?
Okay, so in this question, this is a simple question, right? So here they have just said that when the stress perpendicular to the weld is 65 MPa, it will break. So if you see, the failure plane will be something like this. When the pressure vessel breaks, it will break along these lines. It will break along this line. So the broken part will be something like this. So this is not similar to, this is actually nothing similar to the soil mechanics failure plane or anything like that. It is not the Mohr Coulomb failure plane or something. This is just when it breaks along this direction. But in reality, the conditions are a little different. But this problem states that so here basically these squares are all pulling across each other, right? Inside you have a pressure. You have rigid squares, not rigid, very strong squares. The squares are just attached together. They are pulling along, they are pulling each other. So when the pressure exceeds the maximum value, the joint between the square will break. So basically this squares will come apart. So you can say these are failure planes. These directions are failure, something like that. But those have got nothing to do with the failure plane of the material. It is just because the pressure vessel is constructed in this manner, they are failing across this plane. But are the other concepts okay? Like,
Yes, sir.
yeah, like you had asked for this stress transformation and Mohr circle and this pressure vessel, right? So is this satisfactory? I just want to know, or something more if you want. Okay.
Yes, sir. Understood, sir.
Yeah. So I have another question that maybe you can try in the week and come next session. There's also similar thing here. It is welded. Again, they're asking to find the normal stress perpendicular to the weld, shear stress perpendicular. So you can try this. Shear center, unfortunately, we don't have time today. We'll do it next time. These are some small shapes. You can find out the shear center in this. So again, let me ask, if you have other topics that you like to suggest for the next session, we'll take it up. Any other topics? Doubts in these or other areas? Structures, structural analysis, mathematics.
Sir, in RCC, important topics.
Okay, RCC typically has very low weightage. 1 or 2 questions we have gate, and those questions are quite simple. Mostly and mostly they deal with moment of resistance, shear resistance, bond, and they're not very involved. Usually they take time, so they are usually they're small. Questions in RCC are small. If you want, we can. So any particular topic in RCC? Like if you don't have any doubts in it, we'll just do problems.
Yes,
Okay,
sir.
yeah,
Problems.
problems. Okay, and so maybe we can do 2 or 3 problems from 1 or 2 from moment of resistance, 1 from shear, 1 from torsion or bond. That will help. Okay, that we can do RCC problems. One more, like another feedback I would like to know is today a lot of things, I told a lot of things, but was it repetitive? Did I repeat something that you already know, or you can stop me if you want to skip to the next portion. So these concepts of stress, if you're already familiar with, was anything
No,
repeated?
sir. No,
Okay.
sir. This concept of stresses, I'm not familiar with, but the derivation for that is, I have learned, sir. The derivation,
Okay.
I have learned, sir.
Derivation of the stress transformation.
Mohr circle, that sigma
Mohr
xx.
circle. Okay. Yeah, fine. Yeah. But physically, what stress means that it is important that you achieve. That is why it is. Yeah, this you maybe know. This usually people. It's covered in all syllabus.
Yes,
And that's why I skipped most of it. Right? Only one I did at the other side.
sir, for 2025 gate, will you come, sir?
I'm not sure. Usually, we apply on that portal. We'll say we are interested in helping people. Like we say we are interested in doing TA, they will select us. So it's not in my hands. If they select, I'll be there. If not, we need to see.
Okay, sir. Thank you, sir.
Yeah, thank you. Even if I'm not there, that portal will be open. So you can, that Google Groups, if you're in that, you can post. I'll try to, I may not be able to explain, but I can write something and clarify that.
Thank you, sir.
Yeah, okay, thank you. Any doubts? Okay. Thank you for attending. Let me stop sharing and stop the